research is variable. If you've been conversant with the field of artificial intelligence and machine learning, more especially natural language processing, you must have been aware of a particular research paper titled Attention is All You Need. This particular research work by the Google engineers changed the landscape of natural language processing and sequence-to-sequence models. So like you can see here, this paper was authored by Google engineers. In my last video, I reviewed the abstract of this research work, where I talked about the significance of this new architecture that is being proposed and now in popular use in the field of natural language processing. So I talked about the dominant, sequence-to-sequence transaction models, which has been significantly dominated by convolutional neural network and recurrent neural network. Oftentimes, the best of these architectures always include the encoder-decoder blocks. But in this transformer architecture, we are going to be introducing a new thing to the encoder-decoder blocks, and that is the attention. So this architecture will be based solely on attention mechanisms. This transformer architecture has been experimented on a WMT 2014 dataset for the English to German translation task, achieving a significant 28.4 BLEU scores, and that has been over 2 BLEU scores from the best sequence-to-sequence model before this transformer architecture. And after this task has been trained for 3.5 days on 8 GPUs, it will achieve a state-of-the-art BLEU score of 12.0, which is at a fraction of the cost of the best model before this architecture. Recurrent neural network (LSTMs) GRU have been firmly established as state-of-the-art approaches to sequence modeling. Numerous effort has been experimented to push the boundaries of recurrent language models, encoder-decoder architectures. So, the dominant architecture has been used in this field has been the LSTM, the RNN, the GRU. They've been firmly established as state-of-the-art architectures. But research has, proceeded to see how we can, push the boundary of these architectures, and here we are today. RNN, which consists of, which takes in the input sequence. RNN is a sequence-to-sequence modeling architecture, right? So it takes in the input sequence and generates an output sequence. But we are able to know, of course, we know that it does this, of course, by narrating length parameters from a particular layer, a recurrent network, to the next one, generating the tokens one after the other. And this length information have been transferred sequentially, giving it a major constraint of not being able to apply parallel processing. And this major constraint is one of those things the Google engineers saw and they need to work on. To solve this problem of the inability to train, of the inability to learn from the input sequence in parallel, the Google engineers introduced the attention mechanism. And this attention mechanism, like I said, has become an integral part of compelling sequence modeling and transaction models in various tasks, allowing modeling of dependencies without regard to their distance in the input or output sequence. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. So this is what has been done exactly. Now, with the help of the attention mechanism, we're able to process the input to output sequences, in parallel. And how do we do that? By focusing on different parts of the input sequence with different attention heads. And that's what we are going to later refer to as the multi-headed attention. So in this regard, we're able to connect different instances, different parts of the input sequence, create multiple ways, combinations in which, and create multiple combinations, and also be able to process what word is important to which word within this simple sequence. Which one should be focused on? Take for example, if you have the cat start on the mat, D-T-H-E would have been referred to as a non-significant word in that sentence. What will have been significant to the cat will have been the position where the cat is, and that's the seat, and also on what is it sitting on, and that is the mat. Okay, so the transformer architecture will have provided much more importance to these words, right, rather than any other one. Okay, and this is the importance of the attention mechanism. Being able to focus on different parts, irrespective of their distance, in different parts of the input sequence, irrespective of where it is in the input sequence. So in this work, we propose the transformer, a model architecture excluding recurrence and instead relying entirely on attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state-of-the-art translation quality after being trained for as little as 12 hours on 8 P100 GPUs. So this is what has been done. In this transformer, the model is not focusing, is doing away with the norm, and that is the recurrence sequencing. Okay, so it's doing entirely away with that and focusing squarely on the attention mechanism. Okay, and that's to be able to focus, to put a lot of attention between the input and output sequences. So the transformer allows for more significant parallelization, like I've said earlier, is really able to focus on different areas through the multi-threaded attention and can reach a new state-of-the-art translation quality after being trained for as little as just 12 hours on 8 P100 GPUs. Background. The goal of reducing sequential computation also forms the foundation of the extended neural GPU. So, ByteNet, S2S, all of which use convolutional neural network as basic building block, computing the representation in parallel for all input and output positions. So now this is it. You know, CNN, convolutional neural network, has been used majorly for feature extraction from images, right? But this architecture has been modified for sequence, modern like convex to S. Don't forget that this sequential processing of data, if you try to apply any form of parallelization in this architecture, you are going to be growing in much more amount of data depending on the number of combinations you want to get. So for S to S, you're going to be having a linear increase in the number of combinations. I mean, the more number of combinations you want to have on a particular token in the input sequence will grow logarithmically. Okay, will grow linearly and logarithmically for ByteNet. So as a result, it's going to make it difficult for us to focus on different tokens within the input sequence and make it difficult, right, to learn dependencies between distant positions in the input sequence. So in transformer, this is reduced to a constant number of operations, albeit at the cost of reduced effective resolution due to averaging attention weighted position and effects we counteract with the multi-headed attention as described in section 3.2. So like I've said earlier, the multi-headed attention within the transformer architecture allows the transformer architecture to focus on different parts, press all this information as parallel, focus on different parts of the input tokens, right, irrespective of the position of one to the other. And we'll discuss this in great detail as we proceed. Self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in various tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task-independent sequence representation. So this is basically what this is saying. So self-attention, right, is, and like I have said earlier, the transformer architecture is focusing solely on attention mechanism, doing away with any of those previous mechanisms, the recurrence, the convolutions, and so on, right, that has been used prior to the establishment of this architecture. So it's focusing on attention. So self-attention in itself is just the ability to represent the input sequence, right, in a numerical form, and also to be able to see, okay, so after representing the input sequence in a numerical form, you'll be able to focus on which one is important to which. Like I gave an example earlier. So let's say, for example, the cat sat on the mat. The cat sat on the mat. D is not as important as the position of which that cat is. The cat's position is to sit, and where is it sitting on is the mat. The transformer architecture using this self-attention mechanism will rather focus on cat, mat, and sat rather than D, because D does not provide contextual information to the input sequence. So, and all of this understanding is achieved using the attention mechanism. So, and with this, we've seen that this architecture has been able to successfully, excel in various tasks, such as reading comprehension, abstractive summarization, textual entailment, and learned task-independent sequence representation. End-to-end memory networks are based on recurrent attention mechanism instead of sequence-aligned recurrence. Okay, so I was talking about end-to-end memory networks are based on recurrent attention mechanism instead of sequence-aligned recurrence, and has been shown to perform well on simple language question answering and language modeling tasks. So what we've seen earlier was all these end-to-end architectures like recurrence and the likes. They've done well, right? In simple language question answering and language modeling tasks. So, but to the best of our knowledge, however, the best of the knowledge of these Google engineers, I think it still remains, right? The transformer is the first transaction model relying entirely on self-attention to compute representation of its input and output without using sequence-aligned RNN or convolution. Okay, so it is this transformer alone that has been able to achieve self-attention without using RNN, okay, or sequence or convolution, sequence-aligned RNN or convolutions. Okay, so in this section, we'll describe the transformer, motivate self-attention, and discuss the advantage over models such as what we have in 13, 14, 14, 15, and 8, and that is the RNNs, the ByteNet, and so on. The ByteNet, convex trace, and likes. Now, let's look at the model architecture. So, most competitive neural sequence transaction models have an encoder-decoder structure, right? Most neural sequence transaction models has an encoder-decoder structure. And where the encoder, so this is what the encoder does, right? So when we always talk about transformers, we always talk about encoders, decoder architecture. So what the encoder does is to map out input sequence, okay, to map input sequences into a representation. So transform it to token and map it into a form of representation, right? To a form of continuous representation. And then this particular representation will be given to the decoder, which then generates the output sequence, one element at a time. The decoder is autoregressive. So what we'll be doing there is it will generate the output sequence at each time steps. One after the other. Okay, so at each step, the model is autoregressive, like I said earlier, consuming the previous generated symbols as additional input when generating the next. So there's something we call the look ahead mask. So what we want to do when generating this sequence, one after the other, since this is autoregressive, is to ensure that the previous words, while the model is generating an output for a particular word, it has access to its particular word and the previous words when generating the next word. So what we are going to be doing there is to ensure that the model is not aware of the future words, so we block it, right? We block the future words by multiplying its attention weight with negative infinity, by multiplying its attention scores with negative infinity. So by the time you are going to be applying a soft max activation on it, it's going to scale it down to 0, while the important features are going to be scaled 1. So it is something similar that we also use in the max attention in the encoder section, where we try to mask out the paddings that are used in test processing before training the model. So the transformer follows this architecture using stacked self-attention and pointwise fully connected layers for both encoder and decoder, shown in the left and right halves. So this is what we are looking at. The transformer itself follows this overall architecture, right? Using the stacked self-attention. Okay, using the stacked self-attention. So like I said, the stacked self-attention we are looking at here is called multi-head attention. Okay, and that's because different heads is being able to focus on different parts of the input sequence. Fully connected layers are for both the encoder and decoder. So this pointwise fully connected layer is just basically a dense layer with value activation function. So that's just to connect the encoder, the attention weight that being generated into the fully connected layer, applying red. Red activation function is going to drop everything negative to 0 and keeping only the positive part. And that's just in this particular task, what we are trying to do basically is to filter out the less important words, and that's the point of attention. Less important part of the input sequence. So of course we're going to be doing that with ready. So now so yes, that's what we have. Okay, so fully connected for both. Yeah, so we have the multi attention fully connected FCN, that's fully connected network connected fully connected networks in both the encoder and decoder section. So let's take a look at the encoder and decoder task itself. The encoder is composed. Okay, so the encoder can consist of any number of stacks, right? I built a translation machine translation, that's a language translation project, and I used just full number of encoder stacks. So it can be any number of stacks, but the original number of stacks that was released in this attention is all you need architecture was 6 identical stacks, 6 identical encoder stacks. So each layer, that is each encoder stack, has 2 sublayers. Each of them has 2 sublayers. So the first is the multi-headed self-attention mechanism. So I'm talking about this multi-headed self-attention mechanism as one which stacks the number of heads. Each number of heads is focused on a particular attention. And after that, then we direct the output of that attention we generated there into a pointwise fully connected layer. So the second stack is pointwise. Like I've said, pointwise free connected layer. So you can see that here, that after this attention, once any attention is being added and normalized, then you pass that into a what? A pointwise free connected layer. So we employ residual connection around each of the two sublayers. Okay, so followed by normalization, layer normalization. So this is the input of each that is the input of the sublayer, where this is the function implemented by the sublayer itself, right? So to facilitate the residual connection, the sublayer in the model as well as the embedded layers produce output dimension of what? 512. So this is it. You see, each input token is being represented based on the number of dimensions that we have. Here we have 512 dimensions, right? So that 512 dimension is the number of representation that each input token would be represented as, right? When in the decoder stacks, here we have 6 identical layers. In addition to the sublayers that we had in the encoder, that's the multi-layer attention followed by normalization, the free connected, point-wise free connected layer, and stabilization. In addition to those ones, so what we also have here is another multi-layer attention stack, right? Another multi-layer attention, block. So that's an addition to what we have in the encoder section. So similar to the encoder, so we also apply, we also use the residual connection here as well. Okay, so we modify the self-attention sublayer in the encoder stack to prevent position from attending to subsequent positions. So I talked about this earlier when I was talking about the look ahead mask. Please listen to what I said earlier. So this masking, combined with the fact that the output embedding are outside by one position, ensures that the prediction for position I can only depend on the node output at the position less than I. So this is what it's trying to say. Whenever we are say, for example, let's say we are trying to we have I am going to the market. While I am generating going, I only have access to I and I am, and then the particular position where I am, which is going. So the market is being what? Is being blocked using the look ahead mask. So I've discussed how that is being done earlier. So now let's take a look at the attention itself. How do we achieve this attention? So an attention can be described as mapping query and set of key value pairs to an output. While the query keys values are output and outputs are all vectors. So this is how this works. Q, V, and K. That's query, value, and keys. So let's say, for example, you are trying to search for a particular thing on YouTube. So let's say, for example, transformer architecture by AI research with Farouk. Transformer architecture is a query. That's what you're looking for on YouTube. Okay, but a more detailed explanation of what exactly you are looking for. Not just transformer architecture by any other person, but transformer architecture explanation by what? AI research with Farouk. So that AI research with Farouk is the key because that's what gives more detailed explanation to what the query is. So, and as a result of that, that's the query and that's the key. So that's the description of what the query and the key is. They are vector representation. So what this does is they enable us to be able to query the necessary information that we need from the to query the necessary information we need. Okay, so the first thing we are going to be doing, we look at, okay, so I think we are going to talk about the scale dot product attention after now. So we're going to explain how the attention itself is being achieved. So the output is computed as a weighted sum of the values, where the weights assigned to each value is computed by a compatibility function of the query with the corresponding key. So we look at this. So the first thing that we done when trying to get this attention weight is to first multiply the query by its key. Okay, multiply the query by what? By the transpose of the key. So after which we are going to scale it. We are going to scale. Why? Because when we are multiplying these two vectors, we are performing matrix multiplication dot product. They could be exploding values, right? We could result into exploding values. And in order for us to be able to avoid something of sort, so we are going to scale this by what? By the square root of the dimension of the key. Okay, we are going to scale that by the dimension of the key. So let's take a look at that. So you can see the query and the key. Perform matrix multiplication between both of them, scale both of them, right, by the dimension of the key, and then mask it. Don't forget I said earlier that after this, we are masking. What are we masking with? We are masking by the padded input. So this is what happens when we are pressing these input tokens. So you see that when we have a lot of words, so let's say we are performing a translation task, for example. So you have a particular word, maybe the longest word within one of the input sequences what has 20 tokens. 20 tokens, right? So you want to represent every other sequence, right, to be of the same length of token. So if one of them has 3 tokens, for example, so it will be padded with 17 tokens. So and these 17 tokens are just zeros. They could be anything, but oftentimes we use 0. So let's say 0, for example. these values that are being padded with has no relevance to that particular sentence. So in order for us to ensure that the padded tokens has no importance when computing the attention weight, what we have to do is to ensure that we padded we masked the padded input that we have inside the sequence. So I've made a lot of visual and detailed explanation of this in my implementation of the translation project of Yoruba to English translation task, where I brought out of visual explanation, text explanation, and also the code for implementing this. So I'll be releasing that along with this video once it's I'll be releasing that along with this video so you can go through it as well. So you can see that once we have the verification of the query and the transfer of the key, then we do what? We scaled it with the square root of the dimension of the keys. And then we also mask. So after that, then we now apply soft mask. And how do we mask? Right? How do we mask this particular values? So we mask these particular values. Okay, so we mask these particular values by what? By multiplying them with what? With negative infinity. And as a result of that, by the time you are going to be by the time you are going to be applying softmax, so every padded values will be 0, while the important ones will be 1. Then after doing all of that, then you can see that we now multiply the resulting value. We do a multiplication with the, so what we are going to do after doing that, we do a multiplication of the output of the softmax with the value. Then we get the attention weight. So it is this attention weight that we have at each edge here. Okay. So just blood attention is much faster and more space efficient. So there are other forms, right, of applying this attention. So some use additive attention, and additive attention has been shown to be compatible, complete the compatibility function using feed-forward network with a single hidden layer. So while the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it is implemented using highly optimized matrix multiplication code. So yeah, it is said that the additive attention is not as effective as the dot product attention. As a result, we are using this. So let's take a look at the multi-headed attention. Okay, so here we have it that if the dimension of the key is small, then both additive and dot product attention performs similarly. So that's another thing we have to note. So here we have that instead of performing a single attention, then here we have n number of dimensions based on the heads, right? And it will be found to be beneficial. We found it beneficial to linearly project the key query keys and values h times, that's number of head times, with different length linear projection. So yeah, that's interesting because so based on the number of heads that we're able to split the query key and values into, we're able to get n number of attention weights, and then it makes us to get a much more interesting attention weight using a combination of all of these attention weights length at each instances from the EP sequence. So look at the application of the attention in our model. So number one is that the transformer uses multi-headed attention in 3 different ways. One, the encoder-decoder attention. So we have the encoder-decoder attention, where the queries come from the previous decoded layers, right? The query comes from the previously what? Decoded. So we are getting the query from the previously decoded layer, right? And the memory keys and values come from the output of the encoder. Okay? So the key and value come from the output of the encoder, while the query comes from the previous encoder. Previous decoder. So this allows every position in the decoder to attend to over all positions in the input sequence. So this mimics the typical encoder-decoder attention mechanism in sequence models, such as what we have earlier there. Now, the encoder contains self-attention layers. And in a self-attention layer, all of the keys, values, and queries come from the same place. So in this case, the output of the previous layer in the encoder, each position in the encoder can attend to all positions in the previous layer of the encoder. So this is what this trying to tell us. It's telling us that the encoder contains self-attention themselves, right? Like you can see the encoder, each of them has self-attention. Okay. So in the self-attention layer of the key, value, and queries come from in the self-attention layer. Q, K, and V, that's query, key, and value come from the same place. So in this case, the output of the previous decoder, right? Previous encoder. So the output of the previous encoder, each position of the encoder can attend to all positions. So since we are processing all of this information between the encoder and decoder, getting the output of the previous layer from the decoder as a query and the key value from the encoder, they'll be able to attend to all possible positions within the input sequence. Similarly, self-attention in the decoder allows each position in the decoder to attend to all positions in the encoder up to including the position including that particular position. So when you're in a particular position when generating the output sequence in the decoder, right? So you're able to attend to all possible, inputs you have in the encoder, okay, to generate an output from the decoder stack. So let's take a look at this pointwise feed-forward network. Okay, so another thing I did not mention there is that, like I have said earlier, we apply the local head mask, we multiply that with negative infinity to remove the future words. Because of the priority of the decoder section, we want to generate a word at a time, applying that enables us to block future words and generate and have information to only the token we have in that particular time step and then the previous ones. So that is that. Another thing you're going to be looking at is the pointwise feed-forward network. So like I said earlier, the pointwise feed-forward network is just basically the dense layer with ReLU activation function. So now, embedding and softmax. Similar to other sequence transaction models, we use len embeddings to convert input tokens and output tokens to vector of dimension, right? D model. So we use the usual length, linear transformation, and softmax to convert decoder output to predicted next token probabilities. So what we use here is what? We use linear transformation and softmax, okay, to convert the decoder output to next token probabilities. So in our model, we share same weight matrix between two embedding layers, okay, and the pre-softmax linear transformation. So in the embedding layer, we multiply by what? By square root of the D model. Okay, so we use the linear transformation, that's pointwise feed-forward, along with softmax to convert the decoder output. Don't forget that what we have in the decoder output is what? The attention weight. Okay, the attention weight, we use all of those information to predict the next token probabilities. And once we've gotten the next token probabilities, then we're able to look for their corresponding values. Okay, so we share the same attention matrix between the two embedding layers and the pre-softmax linear transformation. So to generate the next output token. So now let's take a look at the positional encoding. So since our model contains no recurrence, so there's no recurrence. There's no going from one token to the next like that in sequential order. Since we don't have anything of such, so we use positional encoding to be aware of what comes before what. So that is basically what positional encoding does. Okay, so this table shows the maximum path length, good, per layer complexity, and minimum number of sequential operations for different layers, for different layer types. N is the sequence length, and this is the representation dimension. K is the kernel size of the combination, and R is the size of the neighborhood restricted self-attention. Now, if you look at this, self-attention, recurrence, composition, and restricted self-attention. So these are different attention. These are different layer paths, right? Okay, so these are different layer types. So once you look at the number of possible combinations per layer, right? So and if you look at that of the self-attention, so you can see that N here is representing the sequence length. So here we have the square of the sequence length times each dimension. Okay, so the square of the sequence length times what? Times each dimension. So this enables us to be able to what? To process different combinations of our input tokens, right? While generating output. Okay, so now this is what this does. Bottom of the encoder, so the position encoding have the same dimension as the embeddings, so that the two can be summed. There are many choices of position encoding, then of position encoding. So you have len and phase. So len and phase are two types of position encoding you can use. Now this is this. You see, for each don't forget that all our input representation now have the same length. So a particular word, right? Even words are going to be, even tokens are going to be represented as cosine, right? While the odd ones, even one will be represented with sine, right? While the odd ones represented with cosine wave, sinusoidal wave. So using those sinusoidal wave, be able to know which word comes before which. So that's the simplest explanation I can give to how positional encoding learn input representation, positional representation of the tokens. So that's basically that. So in our next video, we are going to be talking about why self-attention to the end of this paper. Thank you. Don't forget to subscribe to this YouTube channel and share.